Well, thank you everybody for coming along today and this afternoon. So just before the weekend. So it's finally sharing the screen here. Incredible. Um, can-
Okay, now it's good.
okay, good. So what I'm talking about today is polymer composites, granular composites. Sorry, particularly looking at the mechanical performance of polymers and polymer bonded explosives. So the reason for doing this is because there are a lot of applications for composites of various natures with polymer binder. Industrially, people want to be able to model the mechanical response of polymers and make a prediction. The military need high rate shock equation of state, but there's also applications such as biomaterials, such as silk, which is a highly crystalline polymer, and things like group interaction modeling have been applied to a number of materials, and again they're trying to extend the range of these kind of modeling processes. So the contents, the techniques you've already seen in the last few lectures, so that should be straightforward. We'll talk about polymers, polymer bond explosives, and then constitutive models. So fairly straightforward. So you've seen this slide before, and we are particularly just reminding ourselves that there is a range of strain rates going from the very slow to the very strong shock, and inertia and various failure processes are important in different regimes. In this kind of study, we look at various types of loading platform, from instroms, or as you would call them, universal testing machines, maybe, going at very low rates where you're doing effectively quasi-static loading. You then go to drop weights up to Hopkinson bars, into small Hopkinson bars, which are useful for very small grain size materials, and then Taylor impact, and finally plate impact. And there's a little comment there basically saying what each one is generally used for. So a polymer bonded explosive or a plastic bonded explosive has particles of explosive in a polymeric binder. And what we see here is an image of a highly loaded, so this is 90% plus, highly loaded polymer containing 90% plus by volume of energetic, and the polymers there, generally you need to add some kind of interfacial agent to get a good bond between the explosive crystals and the polymer. When you have a crack forming in this kind of system at low temperatures, you generally find that in these systems that the cracks and the damage follow along the polymer part, so you're basically tearing the polymer open. So that's a key point in the system. However, when you go to higher rates, you may find that you get cracks forming in different ways, and this one here shows another material with a much larger number of smaller grains, and the crack there is a much more straight line. It's a kind of intermediate state. So this is important in the system, and we look at basic thermal and acoustic properties, and generally we do those under static loads where the mechanical load is generally zero. And we measure things like heat capacity and thermal conductivity, thermal diffusivity in the system. And we can measure those and cross-check them because there are simple relationships between those sets of results. We can also get small slabs of material using ultrasonic transducers, and we can measure the sound speeds and estimate, with knowledge of the density of the material, a modulus of it. So these are some general measurements you would make before going near a high rate facility. And if you're interested in starting to do dynamic studies, you would start with, say, a drop weight system. And here is one that we use quite extensively in the Cavendish laboratory. There's a mirror, there's a drop weight with a transparent anvil, there's a mirror, there's a light source. The light comes in, is reflected from the mirror through the transparent anvils, down, and eventually to the camera. So this allows us to look along the direction of impact. If you look from the side, you can see cracks growing, and this is a high-speed sequence showing 14 images from a sequence where a polymer sample has been impacted and is cracking. That cracking builds up, and we can also see in the next slide, looking from the top down, very similar arrangement. You can see shear bands being formed in the material, and a kind of failure process in the polymer. So you can see very clearly how that's the formation of those bands. If you should then move to Hopkinson bar systems, you then find a range of behaviors in polymers. These graphs here show the response with strain rate of 3 common materials. The first one on the left is polyethylene. The one in the middle is a nylon, and the one on the right is a polyethyl ketone. Each of those points, some of them with very obvious error bars, each of those points represents 10 repeat experiments. The one on the left, the polythene, we see shows a very standard strain rate versus flow stress response. It's rising slowly, and then eventually at a strain rate of 10 to the 3 or so, it suddenly increases in slope. The one in the middle, where the nylon has an increase, but then as you go to the high rates, it falls, the flow strength falls and stays low. And then for the polyethyl ketone, you find that it goes up and then down and then starts to rise again. In all of these cases, this was not due to simply forming cracks in the system. The samples were photographed and were observed to be within the bounds of photography, intact across those strain rates. So something else is happening in the system. So these we've looked at a number of times. Now, as we're putting work into the system, we're obviously changing the temperature. And we have used thermocouples to monitor the temperature rise within polymers, using a very small thermocouple, and seeing what temperature rises we get. And it's not very much. It's of the order of a few degrees. If you use miniature thermocouples on metal, say, you get a really good response. So basically, we've used some high-speed photography and thermal imaging on the system and found a mild temperature rise during the compression process. This is to be expected. Now, that shows you the response of a polymer or a range of polymers. What happens when we use polymers of this nature to form a granular composite? So in this case, we had a 70% ammonium perchlorate, 30% hydroxy-terminated polybutadiene. So this is very much like a propellant style formulation. And we were able to get samples made which had a range of particle sizes, either a median of 3 microns, a median of 8, 30, or 2 to 300 microns. And we did Hopkinson bar studies at room temperature and also at -60. So the response we got for, say, the 3 micron particle size at 20 degrees C in our Hopkinson bar is shown here. This is 3 repeats. You've got the true stress versus true strain, and you've got the sample rising and kind of plateauing a little bit. You've got a lot of Hockenheim Cree oscillations visible on the traces. These are these vibrations due to waves moving down a rod. But basically, you can see it's a quite reproducible system in the at this particular temperature. If you then go and look at the different grain sizes at room temperature, you will get this response. Here we see that the 3 micron, the 8 micron, and the 30 micron particle sizes all behave in an extremely similar fashion. But the 250 micron one, so the one that was between 200 and 300 microns, the 250 micron one is definitively softer, indicating that there is sufficient regions of polymer to allow that much softer response, sufficient thickness of polymer in the polymer regions to allow that kind of response. However, if you go to low temperature, here we see that there is a definitive division in the material response over the particle size. So the polymer and the composition is the same, the fill is the same. However, the particle size here is having a definitive difference. So these are the stress strain curves at -60 at 4,000 per second. Fairly clear that there's something different going on. And if you take those graphs and you plot it against various parameters, and obviously we're dealing with some kind of grain size effect, some kind of particle effect. So you plot against common variables, percentage volume of propellant. Well, in this case, it's all the same. You plot it against maybe surface area per unit volume of the particles, making a guess, and you don't get much of a relationship. However, if you plot it against the flow stress against the reciprocal of the square root of the particle size, and this is a relationship that is very much like a Hall-Petch style model. We point out that these polymer systems do have crystals in them, but they are not crystalline, and the cracks tend to go through the polymer. What we see is there's a relationship there based upon particle size. So from this, we undertook a further series of studies to determine if it was the size of the filler particles or the distance between the filler particles, which was an important controlling factor. The outcome of that was it seems that it is the distance between the particles, so the thickness of the filler, the thickness of the binder has a large controlling effect. If you look a little bit more into the data available, you will find that there is substantial quantities of compression data available in the literature. There is a reasonable amount for polymers on tensile data. The gauge length can be a bit problematic because it is not as easy as a metal to get the sample to fail in the middle or along the nominal gauge length. So we use things like image correlation and high-speed photography to see localization. When we look at shear data, there's far less of it available. So in a practical sense, we need to understand the material response in all of these conditions. So again, using digital speckle photography and correlation techniques, and this is to remind you of that process, we went and done some speckle metrology using Hopkinson bars on polymer bonded sugars. So the speckle pattern was produced using an airbrush, and we did the test to make sure that the paint solvent was having no effect upon the composite. We used a high resolution camera, try and get the maximum number of pixels, and we made sure that the loading rate did not introduce motion blur or significant motion blur into the image. And before loading, a static set of image was taken, and we used those as our comparison during the experiment. And this was to remove any distortion due to the optical system, such as the camera. So we have an input bar, an output bar, and a field of view. So that is what you see on the initial stage of the loading. We have some motion there, some exposure, and what we see during the loading is the pushing in of the bar and the flow of the material in the sample. So the bar moves in a straight line. The sample, as you can see, flows out sideways as it expands. So we're looking at the outer circumference there. If you should take the images and compare the prediction of the strain with that of the speckle measurements, we could see that there was a very strong agreement between the simple Hopkinson bar equations, assuming conservation of volume, and the speckle measurements that were obtained. And this is the graph there. So we know that those independent diagnostics are giving a similar output, which gives us some confidence that things are behaving in a way that we understand. Now, we can also use the Hopkinson bar to do indirect tensile testing. And this is a technique that we found very useful for such systems. It's called the Brazilian test. So we have a load being applied through some curved anvils. There are some very well-defined equations on the curvature of the anvil. And we have a sample that takes the form of a disc. And when we press on the sides of the disc, the material wants to move outwards laterally away from the loading that's being applied, and that produces a tensile region in the geometric center of the sample. So this means we've got a very well-defined failure region. We can examine it at high resolution, we can look at localization, and we can check our analysis method. And down below, I think you can see very palely the equation for that particular arrangement, where P is the load, D is the diameter. We've got B and R, which are the radius of the sample and radius of the anvils. So there's a number of parameters that we can look at there. So this is the kind of image you get. You get the curved anvil, which we can see to the right hand side here. Here is the sample, and as we squeeze in, we get the flow pattern showing the motion away from the system, and from this we can look at the Hopkinson bar stress strain output and determine the shear strength of the material from that output. And again, we can see the motion in the system. We can measure pixel displacement across the image and show the variation with position of the material. And what we find for these type of polymer bonded systems is that fairly straightforward, simple equations that predict the stress existing in a disk under this type of loading match very well with the data that we've obtained. So everything seems to be behaving itself, and that's a good thing. We can look at the stress time results and get those tensile stresses in the sample. And something I mentioned before, if you have a particularly long sample, you can look at the wave propagation speed along that sample. Again, being a polymer, there is a variation, and inertia has to be taken into account as well. So you often find that the first wave that goes through a sample of polymer in a Hopkinson bar will be 10% or so higher than the velocity of any following waves, just due to the inertial effects. We've also done plate impact experiments, and this shows you the general setup of a plate impact. You're firing a projectile out of a gun, measuring its velocity, impacting it, and measuring the stress with a stress gauge, which we discussed in the earlier tutorials. And this shows you the kind of loading you're doing. You've got this impact happening. You've got some lateral release in the middle, in the image in the middle of the slide. You've got your shock state, and you're measuring the shock velocity or the shock stress, and you get a curve that generally has a kink in it, a kind of inflection there. In this case, it is occurring at around about 3 kilometers per second in terms of particle velocity. So basically, we're saying that there is some kind of kink there. It's often often attributed to the free volume, so the gaps between the polymer chains. Although we also point out that the intercept when particle velocity equals 0 almost never equals the ultrasonic sound speed we've measured. There are other things going on. And we've got diffusionless amorphous material, and the rise time of these pulses is always sub-microseconds. So it's something more to do with the polymer structure, and maybe not to do with what we might attribute to free volume. So looking at the microstructure, what factors can we control? What factors are controlling the situation? So one basic point is that in the microstructure, we have a large number of crystals. We've got the space between the crystals. The energetic crystals tend to be hard, mechanically tough, and the polymer is soft. So the thickness of the binder between the crystals is small. What this means is when we apply a stress to the system and produce a strain, what we get is a high rate change in the polymer binder layers. Those are the layers that are accommodating the strain in the system. The explosive crystals will have a very small strain, but nothing like that of the polymers. We're dealing with a difference in strength here of around about 100 to 1,000 times. So the polymer is the thing that gets crushed, and if there are thin layers of polymer accommodating that strain, we will get a very high strain rate locally in those binder layers. So one thing we know about polymers is they change their properties very strongly with temperature. And we know that if we have a high temperature or a low rate of strain, we tend to get failure within the binder. But if we go to low temperature and maybe take the polymer below a glass transition point where it becomes much stronger, or we go to a high rate, we tend to see transgranular failure. So the crack goes straight along through explosive crystals, through the polymer. It doesn't go on a kind of a wandering route. It goes in generally a straight line. And that's because at that point, the binder and the crystal are similar in their strength properties. So this causes us to do two things. Number one, look at the crystal binder adhesion. And number two, to look at the variation in response with temperature. So this was a setup that was developed by Dr. Andrew Williamson, and he had a layer of a binder which was spin coated on there, and this was a particular binder system of interest, and a fairly large crystal of high melting explosive HMX held in place by epoxy was glued on a probe, and that was then kind of bound to the plate. And that was observed from below, and a load was applied, and you kind of get these images from the side showing where the binder is being pulled off the surface, and there you go. And that's a fairly standard test. However, the main thing here is that have to be very careful in these type of measurements, because there's a lot of deformation in the binder. So a lot of the energy and the load we're applying is going into deforming the binder and not necessarily dealing with the adhesion of the system. So in that case, we became very interested in what we call the thermodynamic work of adhesion. We know the surface energies of the HMX crystal. You can look them up. However, those of the binder were not known. So we went and used a thing called a Wilhelmy plate, where you stick a plate into the liquid, you push it down, then you lift it up ever so slowly, and you get a angle between the liquid and the polymer coated plate. And you do this for a number of liquids such as water, glycerol, methyl iodide, and you then can work out through the use of the angle, this is that cos term up above, the surface energy of the liquid. You can then go and do that versus these plates covered with the binder and get the result of the surface energy that the polymer, that the binder coated glass plates are experiencing. This means that we can then look at what's called the pair terms between the different liquids. You can look these up. You can find out what the difference in the surface energy is between the two. So you have to use a range of liquids and then cross compare between them. And when you do this, you will find that the binder we were looking at, NCK10, had a surface energy of around about 42 millinewtons per meter. And that is slightly higher than many other binder systems, but it's fairly similar, it's fairly close. This allowed us to work out, knowing the surface properties of the HMX, that the work of adhesion is around about 80 millinewtons per meter. So what this allows us to understand is the energy term we need to attribute to the binding of the polymer to the crystal. So that was a term that was worked out at room temperature. But what about the temperature effects upon the polymer? So we can perform measurements at a given strain rate and change the temperature. Can you make a generally applicable model? What are the independently measured parameters and which parameters are you getting? And we looked at other areas of research. So we were able, looking at the data that was available, to use the peak of the stress strain curve for this particular polymer bonded explosive. The material was always the same, and very importantly, the failure mechanism is similar or the same across the strain rates. We would like to use the modulus, but split Hopkinson pressure bars are not particularly good for measuring the moduli of material. So we tried the failure stress first because that seemed very reproducible across strain rate and across loading technique. And here we have a series of 10 experiments done at different temperatures. The graph number 1 is at 208 Kelvin. And that shows a fairly high stress to failure, so the material is quite tough. As you increase the temperature, the polymer becomes more pliable, so the failure stress drops. And number 10 was done at 313 Kelvin, and as you see, it's dropped by about a factor of 6 or 7, compared to the one we did at 208 Kelvin. So that is the range of failure of that's the kind of data we're getting. And as you see, the failure stress is round about 0.015 to 0.2 or so true strain, and the stress has a quite clear variation. If we look at that compared to other data in the literature, again we can see the failure strains are pretty much the same between split Hopkinson Pressure Bar in the Cavendish Laboratory, drop weights, a high rate instrom, and then other data from the United States, from other organizations in the UK. We have this kind of dependence. So that shows the effect of strain rate. Now, there is a system based on William Landell Ferry, WLF, which basically relates temperature to strain rate. It was developed by the polymer industry in order to look at the injection molding of components. On the left, we have from the Hopkinson bar. Please look at the way the temperature axis is drawn. On the Hopkinson bar, we have the temperature variation on the true stress to failure. And on the right, we have a graph showing strain rate versus maximum true stress across a range of strain rates. What you see there is a marked similarity in the shape of the graphs. Now, William Landell Ferry has a classic relationship between the temperature rate and the temperature and the strain rate, and you find things like a 10-degree change in the a 20-degree change in temperature is like changing the strain rate by a factor of 10. So if you make a polymer move at a high strain rate, it's effectively the same as a lower strain rate at a much lower temperature when the material is harder. So that's a fact to bear in mind. The relationship between the two is called the shift factor, and it allows you to move between those two spaces, temperature and strain rate. And when you do that, you can combine the data as shown here. So this is the black dots are the Hopkinson bar data, and those have been time shifted to be placed on top of the strain rate data. So what you can see there is the very good degree of correlation between that particular behavior, strain rate, and temperature for the polymer system and for this EDC composite. So what's the theoretical foundation of this type of model? Well, you're taking experience from the polymer industry, temperature and flow, stress, something they deal with every day. They also have knowledge of the chemical structure. They do things like cross-linking, put additives, etc. And they generally use a volume-based model for combining different components. And this is called the group interaction model. And what we see here are the thing in the middle is the potential function. That is what we're aiming at. And there is a list of appropriate references on books down below. And what you see, things like structure, heat capacity, and volume are the things you feed into the system to get the potential function. And from that, you can make a prediction of the engineering moduli, the dissipation, the various moduli, and from that extend to creep, relaxation times, viscosity. So it's quite a powerful model. I myself and others have been using it for a number of years. It's so far worked very well with a great many polymer types. It's not so good on silicon rubbers, but there is not so much data on silicon rubbers to actually compare. And the advantage of this type of model is a lot of the parameters are independently measurable. So you're not simply curve fitting, you can make measurements that you can then put those numbers into the equation and see how well it matches. The important thing here is you need to include the complex loss modulus. What is the energy that you're putting in that goes in the form of temperature into the system, into the form of entropy into the system. You need to include that into it. And what we generally use is a thing called differential mechanical thermal analysis. We take a small sample of the material and you flex it at various frequencies across a range of temperatures. And from that, you can get a nice response graph. So there is a paper. I sent Oleg a copy of it. It's, again, I think from 2009, International Journal of Solids and Structures, which informs you how to use this kind of model. So it can tell you all about the mathematics of it. So on the left here, we have your standard DMTA data. And along with density and composition, you can derive a potential function. And on the right, what we have is strain rate versus yield stress, with the dots being the experimental measurements and the lines being the model's prediction. So that's reasonably good. And you can even do it looking at the compression of HTPB, polymer bonded explosive, and also looking at RDX, HMX crystals. As a model, it doesn't particularly care if it's a polymer or not a polymer. It's good to be an organic molecule with a good shape that is known, but it doesn't have to be particularly a polymer in this system. And what you see there are the lines, predictions, and the dots are the experiments. So that's a quite good correlation between the two. And then one question was, what about the shock conditions? What about the polymer? Well, there was a kink I mentioned in the USUP graph very early on, and I said this is the free volume. So here is an example of a prediction made by this model. This is a prediction. It needs experimental verification. But what we're seeing here is for polystyrene, the normal form of the benzene ring or the benzyl ring on polystyrene, that gives you the pink line. The kind of three-dimensional kind of prismatic structure is the thing that gives us the blue line. Is this model predicting that there is a change in the conformation of the polymers when you get to stresses of around about 50%? Sorry, strains of around about 50%. Well, it's a prediction. It needs experimental verification, but it's the kind of thing you can now think about going to try and measure, maybe using spectroscopy, maybe making some mechanical predictions of what other factors you will see if that particular form exists. What we do know is there is a change in the behavior from the experimental measurements of compression versus stress. What we need, though, is a explanation which is based on some more scientifically determined factors, such as a change in conformation. I'm not saying it's a free volume or something like that. We need to have some different verification. So in conclusion here, and I've been remarkably fast today, so I apologize for that with 65 slides. But in this review, the response of polymers and polymer composites has been shown to be, complex. A number, and this is the important things in red, a number of failure processes can occur. High rate loading heats the material, but also allows less time for sample motion. So in these polymer systems, you will get significant heating in certain regions of the material because of the different mechanical responses of the system. In a variety of polymer composites, the application of temperature time frequency shift has been shown to explain some of the behaviors seen. So we can make a reasonable prediction of, say, flow stress versus strain rate. And that's absolutely fine. But the main challenge in this area remains in quantitatively understanding and measuring a thing we generally call damage included and produced by these loadings, accommodating those into a coherent model. The model I've shown you today shows bulk response predicted from chemical structure and thermal data. It does not include fracture. Because we are so lucky in this particular material choice that we've studied, that the failure stress happens to be fairly consistent, that gave us failure strain happens to be fairly consistent. That gave us a really good way of then investigating the properties in more depth, because we were able to link something back to a similar position. But we were not directly able to predict what that position was. We just happened to measure it. So that is a thing to bear in mind. So we feel we can do a reasonable job on predicting bulk properties and bulk properties of strain rate, but actual damage and cracking and attention to things like adhesion between the polymer and the fibers or the granular filler is still a thing we need to do. So there's still a lot of ongoing research that are out there. You know, we have to look at vibration effects, say in aerospace and other things. So low frequency repetitive loading. We have to look at damaged materials, and that will be a subject of a talk next week. And aging effects. We get plasticizer migration. There's a whole bunch of materials that are added to these polymers to make them work. So things we're particularly aiming at are looking at intelligent design of systems. Can we predict a molecule we could produce and then predict its properties and then go and produce it? Can we target the things we need to produce rather than simply producing them and then measuring them? And hopefully this will result in people making more intelligent choices. So I've got to acknowledge a large number of people who assisted and did a lot of the experiments presented here. Clive Sivia, Steve Grantham, Tim Goldrain, Dave Williamson, Daniel George, Stuart Palmer, all contributed significantly. Thanks to them. And the technicians did a fantastic job in supporting this research. So I think that has got me to the end of that particular system. So I'll try on sharing the screen again. Let's see if it actually wakes up this time. I hope so. No, I'm just going to be a black space. So apologies for that. So thank you, listeners. And can I ask if anybody has any questions? I sent Oleg about 6 papers related to this research, which I hope we can share with people to try and give you some of the background.
Thank you very much, Bill. Thank you very much for continuously nice presentations. And
well, thank you.
May I ask you, may I start the questions? Since at the beginning you were talking about the influence of the whole page law, talking about fine-grained materials. What about your experience in the study of fine-grained materials concerning some specific mechanical response? Because whole page law is very unusual threshold behavior of fine-grained materials, and for instance, in shockwave experiments mainly, did you observe some qualitative difference with ordinary materials, with viscose grain materials?
What we generally found was if the materials had the same volume ratio of components, then under shockwave loading they tended to show very similar behaviors, and the difference in behaviors was more marked in the intermediate rate. It's almost like there's a region where the structure makes a huge where the particle size makes a huge difference, as we saw there at kind of quite a marked variation in particle size at room temperature. Apart from really coarse-grained material, everything behaved very similarly. It was only when we cooled it down and got the particles to be near the polymer near the glass transition point did we see this variation in response. So the one thing, so that gives us some idea. As we go to very, very high rates, that is like making the sample cooler and cooler. But in those situations, the sample is no longer flowing. So inertial confinement happens, it doesn't flow. And so the response tends to be dominated by the volume, percentage volume content of the individual components. So because there are these two, filler and binder, involved, one of them, the binder, will have a marked effect on the mechanical properties if there is sufficient time in order to demonstrate, in order to manifest those effects. But when you go to shock waves, basically there's so little time available to manifest that presence and effect that you just get a volume-based response. If you see where I'm coming from, so it's temperature and strain rate together, and when you go to very high strain rates, you ultimately end up with a volume dependency. In terms of modeling and prediction, things like group interaction modeling tend to do very well under shock conditions. They tend to do very well at low strain rate conditions. But as I indicated at the beginning, in some polymers, there's a marked variation in flow stress with strain rate. And that is difficult to this day for models to really capture. So everything might sound nice, but if you've got a polymer system that has a very non-monotonic change in strength with strain rate, that becomes very difficult to predict.
Okay. Bill, may I come back to my question from some another point of view, because you were talking about energetic materials. Since we could expect, for instance, when we go from coarse grain to fine grain materials, probably qualitative different dynamics of transition from elastic precursor to plastic wave. Yes, we could expect, because we have the violation of cold page too low. And for instance, if we are talking about energetic materials, explosive, for instance, and there is links between non-linearity of elastic precursor decay and hem pikes, for instance, but it's still both open problems concerning the nature of chemical pikes and elastic precursor decay. Do you have some opinion concerning influence of grain science on energetic materials due to the transition from due to the appearance of chemical spike?
Okay. So what we've tended to find, and this is kind of links to one of the talks next week, is in terms of the impact interface. We find that if you've got a polymer bonded system, then the outer part of that polymer bonded system tends to be predominantly polymer. So it's mainly polymer in contact with the impacting plate, or polymer in contact with the container, because the grains tend to be dipped into it. So the first thing is you've got this polymer rich layer, which also means, because it's on the surface, you can have a greater presence of things like voids. So on the impact face, you can have this mainly polymer region. It becomes very stiff under the shock impact and tends to fracture. What we also know is that if you have a very stiff polymer, it's far easier to ignite the energetic material due to the cracks now running through the energetic crystals and not trying to go around them. So where am I going with this? What I'm going to say is, for me, it's very difficult, and I have not done it, very difficult to understand what exactly is happening in the first few millimeters of a shock wave inside one of these polymer bonded explosives, mainly because of the practical issues of what is the composition of that surface, mainly polymer, and then you're transitioning into a mix of polymer and energetic binder, and then we know there's a strain rate variation, and then we know that there are other effects as well. So I'm afraid I can't give you a very clear answer there, because I have not got a clear answer to give. What I can say is I think looking at precursor decay in polymers to start with would be a good thing. And then polymer bonded sugars will be the next step, because you're still not having a chemical reaction. And then polymer bonded explosives. So I would want to do shock experiments on hot and cold. So polymer samples that are heated up, polymer samples that are cooled down. I would like to look at the shock response of those materials first before I give them anything, before I make a prediction. So I'm sorry about that, but I would say I would want to do some experiments with that polymer hot and then shock it, polymer cold, shock it, do a comparison between those two. That would be my first step. And from that, I would then hopefully use the other diagnostics to work out if there is a significant change in the properties, and if there is a precursor decay in polymers. Okay.
Okay, thank you very much. And another our audience, please, questions.
Hello, Bill. I have a question about DIC and split Hopkinson bar.
Yes, yeah, please.
As I remember, you said that results are very similar of DIC and split Hopkinson bar equations, but as I remember, the strain field was quite non-uniform in your picture, on your slide.
That is correct. The strain field generated in, say, a Brazilian test does vary through the sample, but it can be calculated. It has been calculated for our samples. So what I can do is, because I haven't got the data immediately at hand, but in the next talk I give, I will start by showing a digital image correlation of the sample of a Brazilian sample and the calculated field, because I have that in my file somewhere, and I can show you that there's a great degree of similarity between the two. So that gave us the confidence that we could use the stress field. Sorry, the strain field was that predicted by the Brazilian test equations. So we saw that, and that's why we felt we could use that particular analysis, because it was predicting a strain field which we actually saw. That's the relation there. But it is a non-uniform. Frankly, it's a non-uniform stress and strain field in that Brazilian sample. It's not homogeneous across the sample in no way.
I'm talking about previous slide with ordinary split Hopkinson bar test.
Okay. Yeah. So there is the ordinary Hopkinson bar test where you create a sample and the sample flows outwards, and so you get a circumferential expansion. Which is correct. You get a circumferential expansion, and also there's movement as well of the sample, through the camera's field of view. So what this means is you see a response showing. I'll look for it here. You get a response that shows outward motion and lateral motion. So you seem to have these arrows pointing in it. So if I'll get to that one, it's fairly straightforward. Let's get to it. Okay. Yes. So you have the horizontal motion caused by the movement of the bars, and that's what we see here. And we're using this bar as our fiducial marker. So this one is moving, and that's why we get the horizontal motion, shall we say? And then the lateral motion is due to the circumferential expansion in the field of view. So what's along the central axis is coming straight towards the camera, so you don't see any lateral motion, but the ones to the side you see moving sideways. So I think there's a nicer image there. So when we use long specimens, the very long specimens like this one, again, this is not a particularly wonderful image, but on later images of this particular sample, you can see the lateral motion, and then you see the lateral motion far more clearly, and there's a lot of longitudinal motion. So that's why it appears to be kind of non-uniform. It's because you've got this. It's a combination of lateral and longitudinal motion that you're seeing in the system. That's why you get these kind of angled lines, angled flow.
Okay, but
is that okay? Yeah.
But you say that results are in agreement. But as I remember, when you calculate stress and strain fields from Hopkinson bar equations, you suppose that strain field is uniform, but in reality is not. But so the question is, why in the case of non-uniform strain, final results are in agreement with simple Hopkinson bar equations?
Because the size resolution, so it's to do with the sample grain size and the size of the sample. So if you're looking very closely, if we were able to see grain by grain and the binder between them, we would see that non-uniformity of a strain. But when we look out across the whole sample, we're seeing hundreds, if not thousands, of those interactions. So the average effect, and this is this is I mean, you're highlighting the key point. The average effect is we can see volume conservation in the sample, and that's how we got the lateral strain from the simple Hopkinson bar equations. But if I was able to look, or if I set up the system to look in more detail, I would see that it would be the binder where the strain is being absorbed, and the crystals are not doing very much in terms of strain. So it's because of the field of view, the size of the grain size compared to that of the sample, that there appears to be a uniform response. But I fully agree, if we looked in more closely, we would see this non-uniform response.
Okay. And another question, did you do high-speed temperature measurements with, for example, nitrogen-cooled photo detectors or something like that?
We used a thermal imaging camera in order to look at the temperature rise within the surface, and this is the issue, within the surface of the sample, and we found that it was of the order of a few degrees, I mean 3 or 4 degrees, in the split Hopkinson pressure bar, which now when we do those kind of experiments using thermal imaging cameras and thermocouples for metals, we can see we get good agreement between the thermal imaging and the thermocouple embedded in the sample. So that's why we assumed it was having that kind of so we assumed there's a small temperature range within the polymer, but we haven't seen it directly. It's of the order of a few degrees. It's because polymer behavior with temperature is not as straightforward as that of metals. You can stretch polymer, rubber bands, for example. You can stretch rubber bands and they will get cold because of the change of entropy in the system, which is why I mentioned the change in temperature and the change in entropy.
Okay, thank you.
Okay. Oh, you're welcome. I mean, it's a really interesting area, and if during this collaboration we can do some more work on polymers and polymer bonded systems, that would be fantastic to get involved with. Yeah.
I think it's a really interesting field, also with application to composite materials, because we have the polymer matrix. Thank you, Bill. Please, another audience concerning questions. Okay. Of course, I have maybe not question, but remark. Bill, we have good experience concerning the study of thermodynamic properties of fine-grained materials, alloys.
Yeah.
To combine infrared imaging and loading in both conditions. In the following condition, it's quasi-static, cyclic, and dynamic, because infrared camera has at our lab has enough resolution, 10 to minus 3 second probably. That's enough for dynamic loading observations. And what we established for to compare coarse grain and fine grain materials, we found that for fine grain materials, and for the first, it was predicted theoretically due to our understanding of transition from coarse grain to fine grain and the nature of the violation of whole page law, that for fine grain materials, in this condition of the loading, combined with infrared imaging, the dissipation level of energy that we could take by infrared is low in comparison with coarse grain materials.
Okay.
And I think it's could be interesting to continue this research, because still we have interest to fine grain materials, and we are carrying out experiments concerning gigacycle loading of fine grain and coarse grain material with characteristic frequency close to 20,000 hertz. It means that we could keep in mind maybe collaboration in this area concerning fine grain materials.
Okay, no, that would be good, because our loading system using the pulsed electrical power is particularly good for obviously smaller sample sizes. So having a fine grain system would be much better, and we've got quite good optical velocimetry. So this would allow us to do, or at least contribute to that area for sure. Yeah.
Thank you.
Okay.
Another audience, please, questions. Okay, Bill, thank you very much. We are totally agree with you, Doc. Concerning that,
absolutely. The dogs.
Her master needs to relax.
Okay. Okay. Thank you. Okay. Well, everybody have a good weekend, and I'll speak to you next week on Tuesday. Okay. Thank you.
Okay, Bill. Thank you very much. Thank you very much. All the best.
Bye.
Bye bye.
Thank you.
Thank you for lecture. Bon weekend.
Thank you.